Welcome to qnawire.
So this question tells us to assume the distance between the protons in a hydrogen molecule is 0.75 times 10 to the minus 10 meters. We're asked to find the energy of the first excited rotational state. Well, the first thing to note is that because we're looking for rotational energy, we're going to need the moment of inertia. And in order to get the moment of inertia, we're going to need to get a radius. So all we need to do is say that our radius is going to be the distance between the molecules over 2, which is equal to 3.75 times 10 to the minus 11 meters. We also know, this is an equation you can find in textbook along with the derivation, that the allowed rotational energy states that we will call E subscript J is equal to h bar squared over 2 multiplied by the moment of inertia I, and that in turn is multiplied by the angular momentum quantum number J, multiplied by J again, plus 1 all in a bracket. And as you can see, these are quantized by that angular momentum quantum number J. So we can model the hydrogen nuclei as point masses rotating about a point r away, both of mass m. So by that account, we can work out the moment of inertia I per atom or nuclei as being I equals mr squared. However, as we have 2 of those, we know that the total moment of inertia will just be the 2 moments of inertia added together, which will give us 2mr squared. The question asks us for the rotational energy of the first excited state, which will be when J is equal to 1. So we can start plugging in some values. So E subscript 1 will equal, well, we have h bar squared again, over, well, now we have 2 times I, so that will be 2 times 2mr squared, so 4mr squared. Times by J multiplied by J plus 1, so that will be 1 times by 2, so it's just 2. And cancelling down, of course, 2 divided by 4 is just a half, so that will be h bar squared over 2mr squared. For the purposes of this question, we will take the mass of our proton to be equal to 1.67 times 10 to the minus 27 kilograms. So now we can start to plug in some numbers. So E1 will be equal to our reduced Planck's constant squared, so that is 1.0546 times 10 to the minus 34 joule seconds, all squared of course, over 2 times by our mass, which is 1.67 times by 10 to the minus 27 kilograms, times by the radius that we worked out at the start of the question squared, so that will be 3.75 times 10 to the minus 11 meters squared. There we go. And that comes out as 2.368 times 10 to the minus 21 joules. Now, the question does actually just ask us for the answer in joules, but you can also convert to electron volts for a more meaningful energy at the atomic level, which will be just divided by the elementary charge, which is 1.6 times 10 to the minus 19, and that answer will come out as 0.0148 electron volts. In case you ever get a question that will ask you for that value, simply divide by the elementary charge. So part B of this question will ask us for the wavelength of a photon required for a transition between J equals 0 to the J equals 1 states. So we already have the first excited state that we worked out, so let's work out the ground state. Well, seeing from this equation here, having a J value of 0 will simply just mean that the ground state energy will equal 0. So E0 is equal to 0 joules. And as such, the change in energy between the levels, and therefore the energy of the photon between this transition, will simply just equal E1. And we also know that the energy of a photon with respect to its wavelength, E is equal to hc, where c is the speed of light and h is Planck's constant, over the wavelength lambda. So rearranging, we can have lambda is equal to hc over our change in energy levels, which we've established is delta E. So plugging in some numbers there, we get lambda is equal to Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds, times our speed of light in a vacuum, which is 3 times 10 to the 8 meters per second, over our change in energy, which is also equal to E1, so that is 2.368 times 10 to the minus 21 joules, giving us an answer of about 84 micrometers.